Amazon has a number of things that can actually help accelerate your research besides just having computing. So as I mentioned, they have a number of pre-configured machines. So if you want to use TensorFlow and you don't have it set up, and you don't have enough clout to get it set up the way you want, Amazon's got a whole bunch of machine learning instances and, importantly, machine learning libraries. So their AWS machine learning category, if you go into the help for that, you'll find about a whole bunch of stuff where they talk about their resources. They already have pre-trained ML models, so if I want to do a comparison, I might be able to use one of the pre-trained modules. They have a whole bunch of stuff to help evaluate the quality of your measure, and a whole bunch of things built on top of TensorBoard that you can use as well. So as the easiest way to interface with Amazon's machine learning toolbox is through an iJupyter notebook, so inside of Python, right? So you can interactively work with it. So you can be running inside your notebook here, and the back-end computing is all happening on Amazon Cloud. So it makes it very convenient if you're working in that. If you're more of a C++ kind of guy like me, then you fire up a console, you do all this stuff like that. But they've really made it easier for those trying to do the notebook because it's hiding inside of your notebook. And then you can literally do stuff where you're going to upload your model. And given the model, you can use, if you're using cloud-based data, you can basically connect the two of them, and it will generate instances and do all of the processing. One of the companies I've been helping is one's using Azure, one's using AWS for their machine learning stuff. And on that side, they literally have it set up so that as more data comes in, it will spin up new instances to say, okay, I have to process more data coming in to do our machine learning instances. And if they get enough data, they train a new model, which is not actually in this drawing. They come back in, but otherwise you can apply your machine learning model to answer questions for your customers directly, or to do security, which is what both the companies I'm helping are doing. On the other side, before this happens, I can change my computing pipeline, use their code commit pipeline, and basically build it so that it goes back into, in this case, Elastic Compute Reduction engine, which we'll talk about in just a second. So that gives you a very nice way of putting things together. So this is not quite how they're using it, but this was one of Amazon's predefined slides. So if I had some data coming in inventory, I can create an object, and Lambda is their functional evaluation engine that decides whether or not I need to make some changes. And if so, then I can submit a batch job to some level of processing that can then go back out. So if you insert labeled image data, space we work in a lot, you can then take that and then use that for your search results, or use it in one case to go back and relearn new models. Okay, and if I need to, for face stuff and for object recognition, Amazon, like Google now, actually has a recognition engine pre-built with predefined classes that I can use to do certain kinds of computations. So if you need some machine learning to do your work, you might actually be able to just leverage what Amazon's already got built into their recognition engine. It's pretty good. It's not the absolute state of the art, so it's tough to use it as a benchmark comparison. But in a couple of our papers, we've used it as a point of comparison, because you're sort of saying, here is what we get if we do this with Amazon recognition, right, as opposed to what our algorithm does. And for many reviewers, if you can do better than Amazon, it sounds pretty good, right? And there are actually many places where if people have done that, they'd have found out they didn't beat Amazon. So sometimes there's an advantage to actually doing that level of comparison. I'm going to finish up Amazon, then we'll take a break. So I'm going to briefly mention two things. These are actually now things that are related to cloud computing. So these are straight up cloud computing tools. But some people might be afraid of doing cloud computing until you see how easy it is to do. So Elastic MAPREDUCE is a web-based interface and a command line tools for running things what are called Hadoop jobs on EC2. And Hadoop jobs, which I'll talk about in just a second, make it really easy to do certain kinds of parallel processing. And in its simplest form, it's really trivial. And in more advanced forms, it actually allows you to do some interesting things. To do this, all your data is stored in S3. The EMR will monitor your job, shut down machines after using them. There's a small extra charge on top of using EC2 pricing, but it's nothing like if I had used 50 machines, taken the time to spin them up by hand and do a bunch of work. So this can make it all pretty simple. And if you really want to have more control over how Hadoop runs, you can run the cluster manually, and then you don't pay the extra charge. The extra charge is really for them to handle all this. So what is MAPREDUCE? It is a very simple data parallel programming model for large-scale processing with large data sets. It allows you to deal with a bunch of cheap computers Sometimes this can actually be more efficient than trying to deal with a GPU or some of the other things. And I didn't mention that when I was showing you models, but if you need a GPU, you can get GPUs through AWS. So you can do training. Currently, they haven't deployed the newest T1000 or T100 models, but they have the older ones. So I think you can get up to 16 gigs of RAM in your GPU, but not anything larger right now. But, maybe it's just the 8. But so anyhow, MAPREDUCE allows you to do highly distributed processing and it's high availability. So MAPREDUCE was actually pioneered by Google, where it processes currently, well, this is actually a 2-year-old slide, it's probably doing 30 to 40 petabytes of data a day for Google using MAPREDUCE. It is huge inside of what their organization does. It's also really heavily used at places like Amazon, Facebook, Yahoo. Facebook has its own parallel stuff in addition to that, but it's pretty powerful. So at Google, the index construction for Google Search and article clustering for Google News and a bunch of statistical machine translation stuff are all built on top of Hadoop. Right? So they all are running this sort of MAPREDUCE paradigm. And one of the other nice things about it is not only is it highly parallel and scalable, you can actually dynamically scale it based on what resources are available now. And so the index construction might take longer because I needed more machines for news. And I can make those two different processes play off against each other and make it happen. So all of the stuff by doing Yahoo Search and Yahoo spam detection for Yahoo Mail, all of those are also all in Hadoop. So Google obviously is not using it on AWS. I don't know if Yahoo's got their own internal for most of it, but Facebook, data mining, ad optimization, spam detection, all that stuff happens also using this kind of paradigm. And you'll see why, because it's pretty easy to do. So if I have a lot of tasks composed of processing lots of data that produce lots of other data, but in a very structured way, I keep applying the same kind of thing to the same kind of data and sort of put it together, it becomes very easy to use hundreds or even thousands of CPUs. But it has to be that I can structure the code to do that pretty easily, or I'm not going to bother with it. So MAPREDUCE provides some very basic functions for the core structure, and then you can define user-defined functions that will go into the example, and we'll go through an example in a second. It does automatic parallelization distributing. It does most of the communication for you. It's extremely fault tolerant. If a machine goes down in the middle of it, you won't even know. It does all of the I/O scheduling and some level of status and monitoring, not fine-grained. So if I wanted to know the time and processing of every process, it's actually not good for that. It's not designed because it's designed to hide all that from you. But I can get high-level status and monitoring what's going on. It is extremely widely used in research, not just in computer science, but in all kinds of other fields for bioinformatics, particle physics. Right here is a nice recent survey, a reasonably recent survey of its applications in computer science. So if you're looking at how does it get used in different research areas, including maybe yours, you can look at that research link and find out. So let's go through a really simple MAPREDUCE operation and sort of see what it would look like. So if I wanted to do this, everything is broken down into code that lives in one of two things: map or reduce, which is why it's called MAPREDUCE. So map provides a function on individual data in a data set to create a new list of values. So if I think of map as literally a mapping function, a lambda function in Python or in Lisp, I have a function, may or may not have a name, but if I have the function square that takes in one item and squares that item, then the map would return, the map of square to the list 1, 2, 3, 4, 5, would return the list 1, 4, 5, 16, 25. Right? So map is literally an operator. It is in Lisp. It's an operator that applies a function over a list, and it returns a new list. Right? So it's the processing of the data. Reduce combines data in a list to create a new value. So if I have the reduce operator, say sum equals, it'll take each element in the array and it'll return the sum of them as I go plus equals. So if I do reduce of 1, 2, 3, 4, 5, I get 15, the sum of the elements. So if I wanted to do an operation over a very large set of data that squared every item and summed them all up, I could do it using these two functions, map and sum, and I could get the sum of the squares of a whole bunch of data. Okay? And that's it. If I can define my problem and I do my processing as map something over data, and then reduce, okay? Reduce reduces everything it gets in its list to a value. It's not reduce the list to make it smaller. It's reduce it to a value. But if I map this over thousands of items, it's going to use the fact that I can break the item into a bunch of lists, reduce those, and then reduce those again. So if I do lots of operators, it'll satisfy that. If I have these two functions to do a MAPREDUCE inside of AWS, I would go in, I would set up my job name, in this case my job flow, set up this is going to be streaming, which means I write in a step reduced manner and it's going to apply it to everything. I can also have my own custom jar or a pig program, which I'll show you an example in just a second about that as well. It asks me where's the input of the data. So in this case, I'm telling it where to get my data from my local file system. Where I want it output, notice the output is like a bucket. So that's my file system elements I'm going to put it. What is the map function? So in this case, this is an example with a word splitting program. And the reducer is aggregate, which is going to break everything up. And then you can pass in a couple of extra args. After that, I say, well, what's the max number of instances I want to have it run on? I can say 4. I can say 400. Right? If it doesn't need them all, it won't let that happen. I think if you need more than 20, you have to get permission. There's a slightly different interface you have to go through, but for up to 20 or so, it's very easy. And then I say how many instances. Instance pricing and everything is like it was before. After I've done that, it'll put it all together in my job flow, and it'll say it's starting, and I can watch it. And that's it. It is now running that process over many, many pieces of data. And I don't have to worry about how many processes it's using, where the data is coming from. So with a little bit of work to structure your problem as map and reduce, and the map function can actually be pretty simple. So if I was running something that is trying to, for example, do machine learning, map might take the list of data, right, and apply machine learning to it, right, and produce an answer, right? And then I can run a whole bunch of instances that do that, and reduce might be compute average performance. So if the code runs and it says, here's my accuracy, then reduce is, I've taken this big list of data and I've returned it as accuracy numbers, then I can get average accuracy really quick, right? Something like that. Reduce can actually, in a more advanced form, produce tuples, right? So it reduces things to one instance. But if that instance is a pair of numbers, that's allowed too. What it can't be is it doesn't change the size of the list. So it's got to do a dimensionality reduction. So if I have a very large list, I can get it down to 2 items, it'll be okay. So just to give you a feel, you can take almost any research you're doing and probably still get it. Some part of it is MAPREDUCE. Not that the research is inherently about MAPREDUCE, but if you can run an experiment, we talked about all these different designs, you might be running each of those experimental design elements in parallel, and then using reduce as a way of combining the results to put them all together. So why don't we take our break, be back by 5 after. And there's plenty more candy.